Welcome back to our fourth session on topological dynamics. Infinity is one of those concepts that's just tricky, especially when you're in these abstract spaces where you can't just use a ruler. So how do mathematicians get a handle on it? Well, today we're diving back into Gordon Whyburn's classic, Dynamic Topology, to look at two really brilliant and powerful ways they do just that.
So here's the fundamental problem, right? On a good old-fashioned number line, you can say a set is bounded. It has ends. It doesn't just go on forever. But what happens when you're in a more bizarre, more abstract space? Those simple ideas of size and distance just completely fall apart. We need a whole new set of tools. And today, we're going to build two of the most important ones in all of topology.
Okay, so our first path here is a bit of a clever trick. It completely reframes the problem. Instead of trying to measure the size of a set, we ask a totally different question. Can we cover it completely with a collection of other, simpler sets? Kind of like throwing a bunch of blankets on something to make sure it's all covered up. This simple change in perspective, well, it leads us to the incredibly powerful idea of compactness.
Okay, so here's the formal definition, and you really got to pay attention to the wording. The key phrases are every open cover and a finite subcover. This is huge. It doesn't just mean that some infinite covering can be boiled down to a finite one. No, it means that for any possible way you can dream up to cover the set with open sets, you are guaranteed to be able to toss out almost all of them, keep just a finite number, and still have perfect coverage. It's an incredibly strong condition.
Let's try an analogy to really get a feel for this. Imagine you have this huge landscape at night, and you're given an infinite supply of spotlights to light it all up. If that landscape is compact, it means that no matter how you place those infinite spotlights, even if you do it in a really weird, inefficient way, you can always just walk over, turn off all but a handful of them, and the entire landscape will still be perfectly lit. That's what compactness does. It gives you this powerful finiteness property, even when you're dealing with infinite sets.
And this is really the magic trick of compactness in action. We start with our set, K, totally buried under this infinite pile of open sets. It seems unmanageable. But because K is compact, we get to do this incredible simplification. We throw away almost all of those sets, we keep just a finite handful, and boom, the set is still perfectly covered. We've just taken an infinite problem and made it finite. It's an amazing trick.
All right, let's switch gears and look at our second path. This one comes at the problem of infinity from a completely different angle. It's not about covering a set from the outside, it's about looking at what's happening on the inside, how the points within a set can cluster or accumulate together.
So to go down this road, we first have to understand what a limit point is. Just think of it as a point of accumulation. It's a point that a set gets infinitely close to. The idea is, no matter how tiny of a little bubble you draw around a limit point, you're guaranteed to find other points from the set hanging out inside that bubble with it.
And this brings us to the Bolzano-Weierstrass property, which gives us a rock-solid guarantee. A BW set is basically a space where infinity can't run away. If you pick any infinite collection of points from inside that set, it's not allowed to just spread out forever. The set itself forces those points to bunch up somewhere, guaranteeing that they have at least one accumulation point, one limit point, right there inside the set.
So now we've got these two very different ways of taming infinity, right? On one hand, we have compactness, which is all about finite covers. On the other, we have the Bolzano-Weierstrass property, which is all about guaranteed limit points. And, whenever you see something like this in mathematics, two powerful ideas that seem to be tackling the same basic problem, you have to wonder, are they connected?
And the answer is a resounding yes. This is Whyburn's Theorem 4. It turns out that compactness is actually the stronger, more fundamental idea of the two. If you know a set is compact, you automatically know it also has the Bolzano-Weierstrass property. The covering property implies the clustering property.
And the way you prove this is just beautiful. It's a proof by contradiction. So you start by assuming the opposite of what you want to prove. Let's pretend we have a compact set K, and inside it there's an infinite subset E that has no limit point. Okay, well, if there are no limit points, that means for every point in K, we can draw a little open bubble around it that contains at most one point from our infinite set E. Now, if you take all of those little bubbles together, they definitely form an open cover for K. But wait a second, K is compact. That means we only need a finite number of those bubbles to cover the whole thing. And since each bubble has at most one point from E, well, that means E must be finite. And that's a direct contradiction. We started by assuming E was infinite, so our initial assumption had to be wrong. Every compact set must be a BW set.
Okay, so we've established a one-way street. The path of compactness leads directly to the Bolzano-Weierstrass property. But the big question is, can we go the other way? Does the clustering property imply the covering property? Well, under the right conditions, the answer is a huge yes.
So does clustering imply covering? Not always, but it does in spaces that are, let's say, well-behaved. What does that mean? Basically, it means points are nicely separated from each other and the space isn't too big in a specific abstract sense. In these spaces, and the technical terms are T1 and perfectly separable, these two properties become completely equivalent. They're two sides of the same coin.
And here it is, the formal statement of that amazing result, the Borel theorem. And while those conditions, T1 and perfectly separable, sound a little technical, the takeaway is just profound. This is the summit where our two paths meet and become one. It's a cornerstone result showing that these two very different sounding ideas, one about covering, one about clustering, are actually describing the exact same fundamental property in many of the spaces we care about most.
So why does this matter so much? What's the big takeaway here? Well, it means we now have two powerful and often interchangeable tools in our kit. We can look at a problem from the perspective of covers, or we can look at it from the perspective of limit points, and we can choose whichever one makes our life easier. This flexibility gives us a much deeper insight into the basic structure of topological spaces.
So where do we go from here? This profound connection, this equivalence, it's not just some neat intellectual puzzle. As we're going to see, understanding this deep link between covering and clustering is the absolute key to unlocking and proving some of the most beautiful and important theorems in all of topology. Thanks for joining us.